All right. Good afternoon, everybody. So while you had your well-deserved lunch, I totally changed the plan of my lectures. So it's total change of plan now. Remember, I promised this morning not to talk about topology, so I will break this promise. There will be a lot of topology, actually. Instead, there will be significantly lesser symmetries. So the reason for doing this and doing this last minute is that I was influenced by the sessions by Titus and Joel, who introduced all these things like gauge theory, Wilson loop, and all these beautiful concepts, cohomology. And it's kind of very, very tempting and irresistible, in fact, to show that these concepts, which will be here at this school applied to describe the physics of symmetry-protected topological quantum matter, weakly entangled quantum matter, I want to demonstrate that the very same concepts are instrumental to the description of strongly correlated topological matter. So what I'm planning to do is, starting in about 25 minutes or so, I will introduce today some concepts, notably lattice gauge theory, that we need to discuss on Thursday, zeroth order introduction to the physics of tori codes and strong entanglement. And you will hopefully see that the concepts these guys introduced this morning are absolutely key. So it's a kind of very nicely unifying framework we are discussing here. So ideally this works out. Like I said, it was a last minute change. So if I come across a little bit confusing, then attribute it to this last minute spontaneity and ask questions, yeah? But hopefully we'll be halfway clear. So symmetries first, yeah? Let's wrap up what we had this morning. We introduced these 10 different types of symmetries. Let's just briefly recap. Time reversal can be absent or present squaring to -1 or present squaring to +1. The same with charge conjugation symmetry. And depending on the value of these guys, we may have a chiral symmetry or not. And there was this one slight glitch here that if you have neither time reversal nor charge conjugation symmetry, you can have either zero chiral or chiral can be present. So these were the 10 different settings. Now, let's try a little bit about physics. I mean, where are these symmetry classes realized in physical systems? There is actually no strict rule. I mean, the rule of thumb is that when you have charge conjugation symmetry, typically a superconductor is around the corner. Yeah? So C equals 1 or -1 systems usually involve superconducting correlations. Where chirality is concerned, chirality is chirality. I mean, when often relativistic or effectively relativistic systems support a chiral symmetry, right? And we saw that in Titus' talk. Titus discussed SSH. SSH has, at least at criticality, has a linear spectrum, so there is some chirality around the corner. So these are only very vague associations. But you can see that sometimes we have superconductivity present and chiral symmetries. And they appear in pairs, and you then have to deal with the consequences of both of them. Yeah? So this is just a rough idea of where these symmetries are realized. And I hope that we will see examples later in this week, of these types, concrete examples. Now, what else can we say? These symmetries carry totally odd, strange name tags. You see them here. Yeah? Each symmetry has a name. For example, SSH model, no time reversal. I totally messed it up. This is H3. Sorry. So no time reversal, no charge conjugation, but there is a chiral symmetry around. This was this anti-commutativity of the Hamiltonian we saw this morning with the sigma z Pauli operator. And in the jargon of the field, this goes as A3. And it's, of course, not easy to see who and why I came up with this notation. I'll explain that in a second. Yeah? That's that. And what else can we say in very general terms? There's not too many general statements we can make, I mean, without investing more input. But one statement we can make that whenever you have a charge conjugation symmetric Hamiltonian, your spectrum is symmetric relative to 0. It's a hallmark of superconductivity. You know that. And the reason for that is, so systems with C equals plus minus 1 have symmetric spectra. Symmetric spectra. And it's easy enough to understand. Suppose you have such an Hamiltonian and you have an eigenstate with energy epsilon. Then you can consider the state you get when acting on this state with charge conjugation operator, so a unitary times complex conjugation. And you ask yourself what this guy will do if you act with H on it. And now C and H effectively anticommute here. That was this distinguishing property of H. So this is this. And with a minus sign. So you get minus C times, minus epsilon C psi. So for every eigenstate of energy epsilon, you're granted a different eigenstate, because different eigenvalue, of energy minus epsilon. An interesting situation occurs at zero energy. At zero energy, it can happen that these guys, I mean, psi and C psi are degenerate, that they're collinear to each other. Because, I mean, now they have the same eigenvalue, 0 here. And if that happens, then you have a topological zero mode, a protected topological zero mode sitting at zero energy. And I trust that somehow this will pop up in, it should pop up in Titus's talks later. Yeah?
Does that mean that for any on-site potential I can destroy the symmetry? Because then it would not be...
Oh yes, if you realize, this is charge conjugation, but if you're referring to the SSH model from this morning. Yeah, indeed. Yeah, you can. Now you have to get into details. I mean, if you have a protected zero mode sitting somewhere, but you can effectively then gap them pairwise out by searching on such potentials. Yes. Yeah. It can be a Majorana mode, but it can also be a different mode. It need not be Majorana. Certainly, in some cases it's Majorana, but it doesn't have to. Yeah. Good. One more. I mean, again, very, very general and half philosophical remark. In systems where you have charge conjugation symmetry and the spectrum is pairwise organized, so the spectrum looks symmetric. Yeah? You have for any you have a mirror partner here. If you ask what's going on close to zero, empirically, I mean, you very often find that there is strong quantum fluctuations are observed close to zero. That's because when these levels want to push down, the partner comes from the other side, and they are strongly, I mean, they repel and are strongly correlated and so on. So you observe strong quantum fluctuations typically in charge conjugation symmetric states near zero, and that's important, including from an applied perspective. For example, shortly after the first Majoranas were reported, so beautiful zero modes, degenerates sitting to zero, became clear that their physics is easily masked by this quantum interference physics going on. And you may even confuse quantum interference phenomena for the presence of a Majorana. And you have all these things to deal with, yeah? But that's, again, not the main topic here. I just want to mention it quickly that these symmetric points are obviously interesting points of interest in such systems. And finally, let me now tell you how this general symmetry stuff interfaces with topology. Yeah, I will not go into topology now, at least not from this perspective, but how we connect between symmetry classes and topology. And the key here is, well, let's suppose we have an Hamiltonian. Yeah? So discuss now from symmetries to topology. So suppose you have an Hamiltonian, and people actually historically, when symmetries discussion started in the 60s, I mean, people were focusing a lot on the Hamiltonians, but then at some point there came the trivial observation, but consequential, that it's often more productive and fruitful to look at the time evolution operator. Time evolution operator is a somewhat more intuitive guy, and so we take a look at the time evolution generated by such an Hamiltonian, e to the minus I h t, and ask ourselves what we can say about that guy. Yeah? So let's start with something simple. Suppose h is trivial. So we have T, C, and S are 0, all 0. 0, 0, 0. What can we say about our Hamiltonian from a general perspective? Nothing. It's just Hermitian. Yeah? So it's just an Hermitian operator. H equals H dagger. And hence, this beast is unitary. And remember, we agreed to talk about Hilbert spaces of dimension n. So we now have a situation where U is realized is in UN. And so, not very exciting, no? But let's now refine the story a little bit and ask what happens if we switch on time reversal. Yeah, now we switch on time reversal in a squaring to 1 situation. So H 0, 0. H now has the additional symmetry that it in a way commutes with complex conjugation. So you can work and should work in a basis where time reversal really is complex conjugation, and then H is symmetric. Yeah? So it's not symmetric in every basis. In this situation, you don't want to work in a momentum basis. You better go to a real space basis, and then really H becomes H transposed. Now, what is U now? So it's obviously still in UN, but it's in a subset of UN. Yeah? You have to hardwire this condition now into. And the way to think about it is you want to get rid of all those U's which are inverse under transposition. U should be also be U equals U transpose, yeah? So you consider only those unitaries which are symmetric, which means that you want to get rid of all antisymmetric guys. And the mathematical way of describing that is to consider a coset of two groups. You divide out ON. ON are all the antisymmetric, or the guys that are inverse under transposition. And this is a group coset. Now, Maya told me that you will get hardcore group theory this week, right? Oh, you already had group theory? When?
Thursday, Friday, Saturday, and Sunday.
Not all the people.
Not all the people, but
Not everyone.
but are you good with the coset factor quotient group? If not, please come and ask me. I mean, I give you a free lecture on that, but I don't want to do it now. If you are not so familiar with it, just think of it as some effective subset of the unitary group, and this is its name. Yeah? What we are talking about here is a group of unitary and symmetric time evolution operators. No? I just want to mention this question.
Yeah, I asked whether you mean a factor group.
Factor group, yeah. Quotient. I mean, you build the right quotient, you divide out all antisymmetric matrices. Yeah? So, what?
I don't know how this realizes what you were talking about. You want only symmetric ones.
Once again,
So UN over ON effectively gets rid of all the antisymmetric.
all the antisymmetric ones, and you keep the symmetric guys. Yeah. I mean, you simply. The pedestrian way to think about it is write down all symmetric Hamiltonians and exponentiate them, and you will get by definition this space here. It's nothing more than that. Yeah, it's very simple. It's just a fancy name for these. Why do I bring up these fancy names? Because these here are good friends of mathematicians. So mathematicians call this space, or this set here, and that one, these are examples of symmetric spaces. And they were introduced, or their geometry and mathematics was systematically introduced by Cartan in the early 20th century. And Cartan gave them names. For example, this here is a symmetric space of rank n, and it's called A in the mathematician's language. And this here is a symmetric space called A1, and so on. So just brief, why do mathematicians use these names? I mean, they have something to do with classical Lie groups here, with UN, ON, SPN, and they go in the mathematics literature under the names group series A, B, C, and so on. And these are sort of derived. These are spaces derived from these groups. That's where these names come from. Yeah? But let's not worry too much about names. What is important is the following. Symmetric spaces are called symmetric for a reason. They are, in a way, mathematical sets and derived from Lie groups, or they are realized as quotients of Lie groups, that looks the same from every perspective. Yeah? A famous example of a symmetric space is a sphere. You can take a sphere, you look at it from different perspectives, it always looks the same. A symmetric, I give you the realization of a sphere in a sec. So these, the UN is such a space, but it doesn't have any special points, unlike a triangle, which is a corner. Yeah? And second thing that is important, there is only 10 families of symmetric spaces. 10 distinct family of compact, these are all compact symmetric spaces parameterized by a given rank. And these spaces are just those here. Yeah? So for every of these rows here is realized as one of these cosets, or Lie groups or quotients of Lie groups, and they are constructed by arguments similar to the one which I used here. Yeah? You take charge conjugation symmetric Hamiltonian, you exponentiate it, scratch your head, look at it, and you will find it's sitting in some group quotient. And then you open up Cartan and find that this is one of the 10 spaces. Yeah, that's where this correspondence comes from. So a few examples. This here is UN. A3 is U2N. We need we have some chirality here, so we need some kind of particle Polish structure. And we divide out UN times UN. And it goes on like that. Here we had A1, which we just discussed. And these are all these different settings. Yeah? So whenever you have a Hamiltonian, compact Hamiltonian, sorry, not compact, finite dimensional Hamiltonian, you can work out in which of these symmetric spaces its time evolution operator lives. And that is often very useful information to have. Now, how does this, what does it now have to do with topology? Let me illustrate this on one example. Let's really consider A3. A3 was a SSH chain discussed this morning, which lives in U2n over UN times UN. So let's try to understand this and then figure out why topology comes in. So this is now connecting to Titus. Suppose we have an A3 Hamiltonian, and suppose we realize the chiral symmetry by anti-commutativity with Pauli sigma z. Yeah? Then we have a structure H equals, you can go to a Bloch basis if you want, but you don't have to. No matter what you do, you will get something here and something conjugate here. In the simplest case, when you work in a Bloch representation, these will just be complex numbers. Yeah? We saw that. So this is our Hamiltonian. Now suppose we really take this, consider this simple case where we have here some z and here z bar. This is two-dimensional. How can we understand this here? Consider the exponential, e to the I ht. It lives in U2, yeah, because it's two-dimensional complex matrix. So we are, U is element U2. But what we need to get rid of are those elements in U2 which are generated by the diagonal, these sigma 0 and sigma x generators. And each of them generates just a phase, a U1. Are you with me? Yeah? So I want to say that we want to get rid of e to the I here phase and there phase, so we divide out this. Okay? What? This is clear? I mean, this I would like everybody to understand because it's, yeah?
Yeah, but if you by phase on that, you will also affect the sigma x and
Yeah, that's true, but I can absorb them. They are living in this, they are included in this coset. I just want to say that all H's which differ here by some diagonal matrix are effectively to be identified because I can absorb these phases in that. Now, can somebody tell me what this is geometrically? Any idea?
Torus.
Torus? Nope. Almost. Ah, a little richer. You're getting close. Sphere. This is a two-sphere. So how do we see that? Well, there are zillions of different ways of doing that. One would, for example, here to... Now, first of all, let me give you the group theory way. If you take U2 and divide out U1, you are at SU2. And if you take SU2 and remove another U1, you get effectively a sphere. And that is, for example, used in the physics of quantum spin. Yeah? If you have a spin, SU2 degree of freedom, and you forget about its phase, if you want, you live on a Bloch sphere. And that is essentially this beastium. So if this, believe me, this is really the two-sphere. So now we can understand where how topology and all this cohomology stuff and so on creeps in. Because if we now want to kind of classify from a topological perspective what our system is doing, we can first try to understand where the time evolution operator lives. And then we get typically some geometric object. All these guys here have a geometric interpretation along these lines. They are generalized spheres or something like that. And we can then remember that, in fact, our Hamiltonian, if we're dealing with a band insulator, can be Bloch pre-diagonalized. So for each k, the time evolution in this conserved Bloch momentum sector lives in such one of these geometric objects. Huh? So essentially, we have topology is encoded in mappings from D tori, namely the space of these k's here, to, now you might say effectively to these spaces here, but this is not quite true, but into some spaces which are intimately related to these time evolution operators. I'll tell that in a second. They are called Grassmannians. Grassmannians, and they are in one-to-one relation to the time evolution guys of this table here. And you have certain maps of this type, and they classify the topology. So what the Grassmannian is, in distinction to the time evolution operator, was in fact explained in detail on the A3 example this morning. Let me briefly indicate that, and then I will finish with this topology business here. So once you have a Hamiltonian, H, or equivalently a time evolution operator, and now suppose we want to understand topology. It doesn't help so much to stare on the time evolution operator itself. Rather, what you want to do is consider the quantum ground state, quantum many-body ground state of this beast. Yeah? So what we have, given this data in a band insulating situation, we can identify a spectrum, and the spectrum of any of these, by definition, should have a gap. We're dealing with insulators now. So there is a gap here. And then you have n plus levels here and n minus levels here, and they all together add to our n. Yeah? Now, if you can upgrade this to a band structure and say that for each value of k, if you plot a Bloch momentum, you have one of these guys here, and if you plot them all together, you get what we call a band structure. And this band structure is derived from this structure here, which in turn builds on the symmetric space setting. Now, what you want to know is actually how do these ground state spaces the eigenspaces of these Hamiltonian, how do they change under variations of k? And that's what was explained this morning. That's where all these Berry phases and vector potentials and so on creep in. So you start from this data, and it constrains what you can get here. Figure out how these ground states then change with k, and from there work on. I mean, do Berry phases or Berry curvature or God knows what. Yeah. So this is how the connection goes. But it's all derived from this tabular structure. And if you then work out what the consequences are, you find that it, of course, depends on the value of d. This is where dimensionality comes in. Yeah? The topology of these mappings you get depends on what d is. So you start writing down here d's, and starting maybe with 0, 1, 2, 3. And then if you're a cold atom person, you may push it a little bit to 4, 5, 6. And if you're a mathematician, you go to infinity. Yeah? So we can play this. And depending on this data now, this one and that, you get different answers. You can have topology empty, or you can have an integer value topological invariant, or you have a binary invariant, which is -1 or +1. So that you get a table, and this is known as a periodic table of topological insulators, which, will it appear, Titus? He went out. So Titus can't answer, Joel can't answer. Does anybody do it? Oh, I mean,
I would say it would be for sure in the lecture by Andreas.
yeah, of course, he has to do it. Yeah. So you get a table, and let me just give you, the structure. Say here, we saw this morning, you have here in Z invariant in A3, and it's constructed along the ways we have. In class A, which is no symmetry is all, you also have a Z, and then it goes on here like Z. This is one sector, and down here there appear Z2s and so on, and Andreas will explain this. Yeah? So this is how the symmetry concept connects to the topology.
Sorry, question?
Yeah?
Could you explain a bit more what this Riemann?
Yeah, I can do that. Suppose you have the simplest case. No symmetries at all, yeah? If you want to know the full eigenstate, the full set of eigenvectors, you write down UN. It's somewhat confusing. It's again a U, but this is now the, what this means to encode is a total set of normalized eigenvectors in a given Bloch momentum sector of an ordinary Hamiltonian. Now, as was also explained by Titus, if you do some reordering here, nobody gives a damn. This is what he called a gauge symmetry. So this is not so much interest. What is interest is how these are intertwined under your evolution. And so you factor out UN plus, UN minus. And you realize this is symmetric space A3 appearing here now of a certain rank. And that is the one which encodes the topology in this case. And you can do this game for every symmetry class. There is a paper by Martin Zirnbauer and Kennedy, which you don't want, probably, you have to have a good reason to go through this, but 50 pages, hard math. That explains all this step by step, yeah? For us, it's more important to remember this logical sequence. Hamiltonian has certain symmetries, and you go on to time evolution, derive the mathematics of the Grassmannian, and from there on, you consider these maps, classifying maps, and you're there. That's how it goes in topological insulators, yeah?
When you do about this spectra here, you're speaking of the single particle spectrum.
Yes. Yes, it's totally single particle physics. And then you are pushing your, if you ask me, what about interactions? And I have is that the question?
That's the question more or less, because
yeah.
when you try to make the symptoms
right.
from the second complex.
They are very good. There are different ways of doing, one route to understanding topology is by anomaly physics, and I trust that Joel will do this. So anomalies, the structure of anomalies is again prescribed by this topological data, but the advantage there is they are perturbatively stable to all kinds of things, including interactions. So that's, I think, is the best way of wriggling yourself out of such questions. Yeah. So that's, yeah.
So if I understand the analysis of the symmetry, it does not have any dimension attached to it.
No.
It's always free. Then the dimension enters only to the Grassmannian.
And this K mapping here. Yeah. So remember this morning when I introduced this block diagonal structure in this. So the way you should think of it is if you have translation invariant, you have relatively tiny for each k. So these blocks are now for each k, yeah? And your symmetries often operate within one k sector. Sometimes they flip. They go from k to minus k.
But the gap is just an assumption, right?
Yeah. And you actually don't need it. That is, you could ask a question, you can ask what happens if I put this order in, for example. If I put this order, then there will be impurity states everywhere, but at the same time you would say topology should be reasonably robust. So if you have such generalized situations, you still have some topology sitting in the background, it will survive. But then you have to apply different concepts. You cannot no longer work with these tori here. You rather ask yourself what happens if I apply some gauge fluxes and some stuff like that. Twists and boundary conditions. So the gap, that's often, again, a frequent source of, some misconceptions. Sometimes people always say that you absolutely have to have a gap, yeah, in a topology, which is nonsense. Integer quantum Hall effect has by definition no gap because it's stabilized by this order, so there's states everywhere. And yet it is arguably topological. So that is more like a mathematical vehicle, this kind of.
Maybe I have the same question as the previous lecture, but
Mm-hmm.
in higher dimensions, the manifolds will be higher dimensional manifolds, and the
Yeah.
single topological invariant will not suffice to characterize it.
Yeah, that can also happen. But then you can often, that's absolutely true. For example, often you have a situation where you have some factor to, but you are still in a situation where you can reduce the problem into different blocks, and there may be more than one of them, and they have their own topology going on. But what is important is that the principle, the raw data, maps from into Grassmannians derived from symmetric spaces. For that, you get away with integer invariance, which is, actually, yeah, simplifies matter a lot. But there may be more than one of them. Yeah? That was, I think, should carry for the rest of this week where symmetries are concerned. If not, we can ask questions. And so I would then close the symmetry chapter, unless there are further questions. Nope. How much time do I have? 17. 17. Yeah. Time is running. Okay. To be honest, I'm not sure I will push through with what I have in mind. Oh?
So you have more.
Okay.
So you have 25 again.
How much?
25.
25. That's good. So what I want to do is, like I said, I want to introduce some concepts relevant to the description of strongly correlated matter. And strongly correlated matter is arguably much more complicated than topological insulators, stuff like that. And I don't understand it very well myself. But I want to introduce some introductory concepts. And, not in a theorem, lemma way, but rather throw some ideas at you. And like I said, I did this because it really, I think the ideas connect very well to what other speakers are doing. And the story starts like this. It starts in 1971. In 1971, beginning of the 70s, there was this famous paper by Kostelitz and Thouless came around out at that time. But there was another paper by Franz Wigner, and let me read the title because you remember how topology lectures are always introduced in the 2000s or last century. We had this Landau paradigm. There were phase transitions, symmetry breaking, order parameter, and now we are also modern because now there is topology and we don't need order parameters anymore. Yeah, that's the way it's introduced. Now, 1971. Duality in generalized Ising models and phase transitions without local order parameters. That was a paper by Wigner. And the introduction reads every bit, you can test me, it reads like a modern introduction to topological matter. So this paper, from my understanding, is every bit as revolutionary as as Kosterlitz and Thouless was, only that it was the ancestor. It came 4 or 5 decades too early, right? It was the ancestor of strongly correlated topological matter. What Wigner did in this paper is he essentially introduced the toric code. So the progress later was, where toric code is concerned, was incremental. The toric code is there in this paper. So, I explain what's in there. Now the time goes on. In 1979, Kogut wrote this famous review on lattice gauge theory. Everybody who wants to learn about lattice gauge theory has to read Kogut. So Kogut starts this review by saying there is this fantastic paper by Wigner, 8 years old, and nobody knows about it. It's just forgotten classic. So what he does in this review, 2/3 of it are reviewing Wigner. I mean, Wigner doesn't write very reader-friendly usually, but Kogut explained it, what's in this paper. And essentially, to explain Wigner, he, as a prelude to that, he introduced or reviewed lattice gauge theory, standard lattice gauge theory formulation of electrodynamics. So that's what I want to do with you. I want to quickly introduce some ideas today of lattice gauge theory, putting electromagnetic fields on a lattice, and that's where all these Wilson loops and gauge fields come in. And on Thursday, we then consider the case where instead of U1 gauge symmetry, we consider Z2. Yeah, U1 is a gauge group, but you can, instead of U1, like our beloved U1, right, quantum phase, we can also consider the very, very simple group Z2 as a gauge group. And if we do that on a lattice, hell breaks loose and we get strong entanglement and topological order and all these things. Yeah? So that is what Wigner talks about. So today we introduced just some ideas of lattice gauge theory more or less in general, and on Thursday, toric code physics, and you will see that this cohomology and gauge theory and so on is all instrumental. So that's essentially the story. And again, I mean, let me emphasize, if I'm not clear, please do interrupt. I need to switch to a different set of lecture notes. Yeah. So let me, because I mean, time is short, I don't want to give you, obviously, not a formal introduction to lattice gauge theory, but just give you some ideas. Yeah. So what is lattice gauge theory all about, and why is it more interesting than classical electromagnetism? So this is lattice gauge. In a nutshell. And everybody, and you are strongly encouraged to do that, who wants to read more about it, consult Kogut 79. He explains this beautifully. It's still the state-of-the-art reference in that business. So what do we do is we consider a lattice. And the lattice, where it's about electromagnetism, is assumed to be four-dimensional. I draw 2 dimensions, yeah? 4-dimensional lattice. And the notation here will be informal. So I'm all 2 pi's and so on are set to unity, electron charge to unity, everything unity. I just want to give you some ideas. On the lattice links, we introduce now our degrees of freedom, which are phases. Phases. So on each link, there lives if we have here 1 link, there is a phase sitting there from 0 to 2 pi. These are our degrees of freedom. And now you want to introduce an Hamiltonian that has a local gauge invariance, that is invariant under locally under a gauge kind of symmetry, if you want, or gauge freedom, which I'll define in a second. And it is constructed as follows. You give these many, many phases an action. So we don't talk literally about the Hamiltonian, we talk about an Euclidean action. And what is this action? It depends on all the phases and nothing more. And very simple, there is a coupling constant here, which will pop up somewhat later. And then you declare the following. You sum you sum over all space-time plaquettes of your lattice. So, for example, this one and the others in the different dimensions. So you sum over all plaquettes. And once you have a plaquette, what you do is you consider the product of all exponentiated phases. That's what you do. So product of e to the I theta mu. And they also depend on the base point here. Theta mu of n. Right? So that is what we can do. And now comes the gauge symmetry. The central object that enters here in this Hamiltonian are the exponentiated phases. Yeah, so these e to the I. They are the key degrees of freedom sitting here. And the Hamiltonian is now made such that it is invariant under a transformation where at each lattice point you independently apply a phase transformation. You apply a phase. So in the following sense, if you introduce here at each of these guys, you introduce a phase degree of freedom, and the way it acts now, these phase degrees of freedom are now such that e to the I theta mu n goes to e to the I chi n theta mu n e to the minus I chi n plus 1. So we apply this to this phase here. We apply e to the I chi here and e to the minus I chi here. This is, the natural thing you would do in this setting. Then this action here is invariant. It's invariant under this because if you do that, you can see it, right? All the phases you put here and here, they cancel out in this product. Yeah, is that clear? The notation is really very, it's just a skeleton notation, but I hope I made it clear. So there's a local high degree of symmetry or redundancy in the description. You write down this beast here, and you can now multiply your system. You can multiply it at each side. You can apply such a phase transformation, and the action doesn't change. Yeah.
So what exactly is a plaquette now? So I have the point n as the starting
Yeah.
point, and then all 8 connections.
Yeah, the plaquette is this here.
Right.
That is a plaquette. E to the I theta here, 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 and here. And if you hit here with this phase, it will multiply here with e to the I chi and here with e to I minus chi. So that's why they all drop out. Yeah?
So chi only comes in this crossing where they cross.
Yeah, chi is defined as the crossings here. At each crossing, you dial up a chi. Yeah, independently. That's important. Independently, you have each chi. And the description is made such that they cancel out. And, yeah.
Is this a restriction? Why when I go from n to n plus 1, the chi is the same and not different?
No, it's not the same. This is a different one. So here I have n plus 1, say. So this one, this link here will be multiplied in this way.
But the minus 1 will appear plus.
Yeah, here you have another link, and that one gets this guy, but with a plus sign. Yeah, it's good that you ask. It takes some time to get used to it, but at the bottom line we have this action here, and we have this. Yeah.
So the action, like that, works in the end, or?
Yeah. Yeah. Of course, it's a free country. I can write it down. The question is, do I get anything useful out of it? And the answer is a strong yes. This is a very interesting beast here to consider. This action actually is a U1 version of what in QCDs are lattice gauge actions. Yeah? There you consider SU2 or SU3 gauge fields. This is the U1 version of lattice gauge theory in general. So now, what can we expect from this action? It all depends on the value of this G. So what I want to convince you of is that there are actually 2 phases realized in the system, and there's a phase transition between them. Suppose G is very, very small, yeah, 10 to the minus 8. Then you absolutely cannot tolerate strong fluctuations of these thetas. So the they shouldn't fluctuate too much because you have to pay an exponential price in action. So if G is much, much less than 1, you have weak fluctuations, theta fluctuations. Now you ask yourself, what could I get possibly in this limit? The degrees of freedom are these theta guys. So we have real value degrees of freedom, and we have a phase gauge symmetry. So chances are that we get classical electromagnetism in this limit. And you know, the analogy you want to draw is up to a constant. Think of these here as line integrals of a vector potential from here to here. Yeah, that's it. I make this a little bit more explicit. So in this limit, we get classical electromagnetism. That's the boring limit, if you want. The more interesting limit is G much stronger than 1, much larger. If G is much larger than 1, the phases can fluctuate like hell. And in this limit, we get a different phase. So in the QCD context, this is the, and I explain why this is the confinement phase, where, which you don't have in classical electromagnetism, but which you have here in this lattice U1. So the difference between this here, which sometimes is called compact electrodynamics, is that it has such a confinement phase. And on Thursday, where we replace these thetas here by binary degrees of freedom, which can take only the values plus and minus 1, the situation will be that this here is defined as strongly entangled spin liquid phase or Toricode phase or so on. Yeah? So that's where it's going, essentially. So let me now quickly explain how we can get a grip of these different phases. I mean, what are we supposed to do? And let's start with this one, G much smaller than 1, yeah?
Sorry, how is G connected to the fluctuations?
Oh, suppose I send G to infinity, yeah? Then my action is 0. Because these are compact degrees of freedom. So now what a partition sum does, I mean, if you think about it in the StatMac, did I tell you this is a classical system? So then I'm supposed to integrate over all theta e to the minus s of theta. Then I can do whatever I want. I don't pay. But if it is in the other limit, I get strong exponential suppression from here. And that is the electrodynamics limit.
How can you then physically interrupt the... I'm getting this mathematical thing, but what's like the physical meaning of G?
Oh, that's in QCD, it would be some QCD coupling constant, and for us, it's just a parameter. Model, yeah, absolutely. No, yeah, sure, that's an important question. So, very, very quickly, how can we understand that what this has to do with electromagnetism? It goes like this. You draw an identification, theta mu n. So this should be essentially like you want to identify it with a tiny line integral of a vector potential. So you write it, you say A is almost constant on one of these links. So you get, if you have here a lattice spacing A, you just write A for line integral, vector potential, and then for the fun of it, you define here a factor G in. And now let's suppose we take the limit of very small g. What we can then do is we can Taylor expand. Because these fluctuations should be e to the I of this, should be small. We Taylor expand. And then you will see here, you get essentially an A here minus this, very close by A here. So this gives you a derivative in the y direction of AX. So you can smell probably that you get something like curl of this A out, yeah? So believe me that if you do the calculation, in the limit g much, much smaller than 1, this becomes minus 1/4 integral d4x. You go to a continuum limit, in this case, yeah, every weak fluctuations. And then you have here d mu a nu minus d mu a mu squared. And that is the action, standard plain vanilla action of electrodynamics. Is the idea clear? Weak fluctuations in this lattice system. You do this identification. You recover or you conclude that in this phase, I get essentially the description of classical electromagnetism on a lattice. Or no longer on a lattice, now I've taken a continuum limit. Hmm? So, and if, yeah, I mean, if we had just the continuum, this would be it. But now we introduced our lattice and can consider the opposite limit, where something else happens. And what this else is, how much time? The chairman? Huh? 10 minutes? Oh, good, yeah. It's more than enough. Yeah. Yeah, exactly. You Taylor expand. You use this to Taylor expand. And actually, you need to go to second order. And then you discover you have discrete differences from different links, and you introduce a derivative. And all g's in the end cancel out. That's how it was made, yeah. Mm-hmm.
So the second limit would be your lattice going to 0.
Yeah, you do that as well. I mean, you can precisely. So lattice spacing to 0 and then taking a continuum limit. Yeah. So that was just to convince you that there is a known limit in this model, yeah? But now there is something more interesting going on. If we go to the other limit, G much bigger than 1, which is called the strong coupling limit in the jargon of theory. And to understand what's happening there, we first have to formulate a good question to ask to the model. I mean, we suspect there is a phase transition. So if there's a phase transition, we should ask in what observables will this phase transition manifest itself. And good observables should be gauge invariant. So they should not change under this redundant chi transformation. And the good observables in this business are called Wilson loops. And they were introduced twice this morning. So what is a Wilson loop? It's like this. Suppose here, so this is a two-dimensional real space section of our model. Yeah? And now I introduce here a third direction, which you should identify as time. It need not be like this, but this is the way I want to consider. So this is a three-dimensional section of our four-dimensional lattice. And now let's introduce a loop. A loop like this. Which cuts here, so it's a loop in space and time, yeah? And there is here a real space separation R in this lattice. And here I have some giant separation in time space, and let me call this beta. Okay? Now, what do we do along these loops? We multiply all the e to the I thetas along this loop. We consider a giant closed loop of, so here, it's symbolic, yeah? I mean, here you have product e to the I thetas along this loop. So here you go in a time direction, space is constant, and here you have a spatial direction, go back e to the I theta. And that is a Wilson loop, and it's gauge invariant because if you introduce all your different chi's, they will just cancel out along the way. So this is a good observable to consider. Yeah. Now, suppose we ask now what is the expectation value of this L. So we take this product, lots of e to the I thetas, put it under our functional integral, so or partition sum under this beast. L. So here you have the product of lots of thetas. Now let's try to think what happens. In this, if you want to understand this fate, we again have to consider these two limits. The first one, which we just discussed, where the phase fluctuations are very, very small, which actually now is a difficult limit. It's easier to understand what happens in the limit of strong coupling, where the phases fluctuate like crazy, because you have here very, very small prefactor. So let's try to understand what happens in this limit. So suppose G is 0, yeah? Then you basically have no action at all. And you integrate over lots of isolated I thetas. What comes out? What do you get as an answer? If you integrate e to the I thetas? 0. Yeah? The loop dies. So in the infinite coupling limit, the loop is just dead. Yeah? And that tells us that something interesting may go on. Now let's try to help it to survive. Yeah? So the way to make this loop survive is to, remember here we have all these products, we have here these tiny little cells. And what we have here is just the sum of all these different phase integrals. So in order to help the loop to survive, we should Taylor expand from the action. We should Taylor expand and bring down as many plaquettes as we need to essentially tile this entire loop here with lots of little plaquettes. Because if we do that, something interesting happens. And you see here in the interior, these e to the I thetas all cancel out. And the loops themselves have a perimeter, and this perimeter is also e to the I thetas, and they are made just such that they cancel against these I thetas from the loop observable. Was it too quick? Okay. So let's suppose we do something simpler. We just take a very simple Wilson loop, which just goes around 4 plaquettes. Yeah. So the Wilson loop is just here theta 1, theta 2, theta 3, until theta 8. So we have e to the I theta 1 to theta 8. And if we integrate over all these, we get 0. Yeah? Now, in the action, we have e to the 1 over g times this product of thetas. So we can bring down now, in order to save this guy from the action, we bring down e to this plaquette operator from the action, which contains theta 7 and theta 6, but with a different sign. E to the minus I theta 7, minus I theta 6, and then 2 more phases sitting here and here. These guys. Is that okay? You just bring them now. Now you see that the loop is very happy about that because 2 of its phases cancel out. So these are these counter-propagating phases here and here. So that you have unity now standing. But in addition, from this loop, you have minus I thetas and minus I theta. So these guys are still uncompensated. But now you bring down the next plaquette, which you Taylor expansion, and this phase will now cancel out, and these outer phases as well. And in the end, if you bring down 1, 2, 3, 4 plaquette operators from the action, all phases pre-exponentially cancel out, and you just get unity pre-exponential. Is that clear? I see questioning faces. Should I explain it again? I mean, I think it's not rocket science. I mean, remember that the action was this very simple expression, 1 over g squared product of e to the I theta along the plaquettes and sum over all plaquettes. So use this, maybe with a minus sign, to kill these phases here. The essential thing, and that is, I mean, these are details, yeah? The essential thing is that in order to make this survive, you have to bring down as many plaquettes as your loop has an area. That's the price you have to pay. For each guy you bring down, you pay one of these terribly small factors, yeah? So the expectation value will be proportional to 1 over g squared to the power of the area of the loop. The area here in this case would be 1, 2, 3, 4, 5, 6 times maybe 15. Yeah? So you would need to bring down 30 loops corresponding to the area of the loop to make it survive. And that is called, in QCD, is called an area law. So this is called the area law. The expectation value of a Wilson loop scales as e to the minus log g squared, which is a terribly large number, times the area of the loop. Okay? That is area law. Now we can ask what happens, switch gears, what happens to the loop in the weak coupling case, which we mentioned before, this electrodynamics case. And I don't want to go there into details, but what you find that in this case, the loop expectation value is proportional to the perimeter of the loop. It's just the perimeter you have to pay. This is called the perimeter law. So for weak coupling, you get a price, you have to price which scales with e to the some constant times the perimeter, which is the spatial separation times beta. Beta times r, yeah? So that is this other limit. And there is some physics here, right, I mean, 1 or 2 sentences. So in the electrodynamics context, what is the meaning of this loop? You see, think of it like this. Time goes on here, and you have here 2 points in space, which are frozen. And I mean, believe me, I can ask a question, I mean, I can explain. What we're actually probing with this loop is the expectation value of 2 static charges in the electrodynamics length sitting here, yeah? 2 static charges frozen in space, and they just sit there, and time goes on. So what this perimeter law, what you get here, is there are some corrections to that. What you essentially get is a Coulomb law. Yeah? So you find that this expectation value, essentially this tells you this 1 over r Coulomb law. The other limit, the area law, in the phase transition, that actually, for that you have to pay much more in a sense. You have this area law, and that is the physics of quark confinement. I mean, if you do lattice gauge theory in real QCD context, you will find that the action now scales with the area, and that means that you have to pay linearly in this distance because the area increases with r, yeah? And this is confinement in QCD. So if you take 2 charges, gauged quarks, and pull them apart, and you are in the strong confinement phase, QCD confinement phase, you have to pay this. And this is, in fact, what I told you is in a nutshell, is the physics of the QCD phase transition. I mean, all very quick, but just the ideas, yeah? What I would like to discuss on Thursday, and you can actually forget all I said so far. I will bring up some analogies on Thursday, yeah, which connect to this picture, is that if we replace this e to the I thetas by plus minus 1s, then the situation is such that the weak coupling phase here is, it's just a phase. But the interesting one is the strong coupling phase. And the strong coupling phase, actually the ground state, quantum ground state in the strong coupling phase is a toric code. So there's a beautiful connection between all these concepts. And that may have been a little quick now. I will recap that on Thursday and hope we will make it in time. Thanks.
Questions for Dr. Yes.
Yeah.
Sorry, was there? So Coulomb law, you're saying, okay, but Coulomb law is 1 over r typically, so
yeah.
How do you go to the first power of the
Yeah, very good. It's an excellent question. You recover the Coulomb law in the temperature. I'm on an Euclidean lattice here. Yes. And the Coulomb law comes out as a correction term, which survives in the t to 0 limit when this one here drops out. I can.
So it's actually this is the 0th order.
This 0th order Coulomb law is the next one. Yeah, absolutely. Yeah. Hmm? Yeah, very good. Yeah.
I'm not sure that I quite followed you, but
yeah.
This is kind of a RG scheme that you're trying to solve?
No, it's much more simple. Suppose you have a magnet, yeah, and you have never heard about magnets before, and you somehow suspect there are 2 phases. The guy behaves somehow different. And then you want to couple up with an observable, which actually indicates these phases, and this observable is magnetization in this case, yeah. So in one phase you have 0 magnetization, in the other one you have 1. Now here in this business, the situation is similar. You have an action, you stare at it, and you think, aha, if you have G large or small, it must behave very, very different. But you still need an observable to indicate that there's actually something different. There's a phase transition going on. And this is your observable in this case. And it's just designed to be invariant under this gauge symmetry we have. And now I've shown to you that in these 2 limits, G much smaller than 1, or not shown, I mean indicated, yeah? G much smaller than 1 and larger than 1, it behaves dramatically different. You have here an area versus perimeter, and there is no continuous way of interpolating between the two. So there must be a phase transition sitting. Again, it's just the words I'm throwing into, but this is how the philosophy. So you can do RG and should do RG to actually go close to the phase transition. Yeah, but that's a difficult problem, and I don't want to touch it.
Maybe you can approach.
Yeah, please. I mean, ask if there's interest, you can ask questions.